Hello everyone and welcome to the Mathematics Bridge course. My name is Prathamesh and I'll be taking part of the bridge course that includes the following topics: permutations and combinations, the binomial theorem, probability and statistics. So let's start off with the first chapter, permutations and combinations. So permutations and combinations is also known as the field of combinatorics in mathematics. It deals with basically the counting and arrangement of objects in a given system. So we all know how to count or arrange, but PNC deals with counting and arranging in a systematic manner, and how to apply the logic of counting to very complex situations, which we'll see in some while. As to how this chapter is particularly beneficial to your maths bridge course and to your college maths courses, so through permutations and combinations, we will also, this topic will essentially aid our probability course. There are quite a lot of problems in probability that can be made easy with PNC. And in your college maths course, you may encounter a few examples in linear algebra which require counting the number of objects in a given space or the dimensionality of a given space. But either way, the probability that you will be learning in the bridge course, in that is the 11th 12th HSC um, maths, will be the building block of your engineering statistics course. So if you'd like, you can also refer to the HSC 11th and 12th maths textbooks. The chapter permutations and combinations is included in the second part of the 11th HSC textbook. Okay, so that being said, let's start with PNC. Now, before understanding what a permutation or a combination means, let's start off by learning how to count. Learning how to count again systematically. So, imagine that I have to go from the place A to C. Okay, you can imagine A, B, C as anything. Perhaps A is your home, B is the nearest station to you, and C is your college, ICT, something like that. Let's say that's just what this is. Okay. Now you want to know how many routes exist of going from your home to ICT, and all of these routes are such that you first go to the station and then you go to your college. So let's say that going from A to B, there are three possible routes. They can be, say, auto, metro, or bus. I'm only naming these routes so that it becomes easier to count later on. And from the station to ICT, perhaps you can go by metro or by the train, local. Now, if you want to count the total number of ways, let's say that is n. Total number of ways to go from A to C. Now, the most obvious logical approach is to simply count, because this is a sort of simple case. So one possibility is, if I take the auto from A to B, I can either go by metro or train. So this is, say, this represents the auto plus metro possibility. This is the auto plus train, and similarly you can take not metro, or say you can just walk. It's metro twice, so say from A to B, the other option is to walk. So if you can take a walk and then the metro, or walk and train, right? And similarly bus plus metro or bus plus train. So this is 1 added 6 times 6, right? You can also remove the brackets. So 6 is the same as 1 plus 1 plus 1. Now if you look carefully, you will notice that this is the product of 3 times 2. In other words, this is the product of n a to b and n b to c. That is why I wrote, I added in this format by putting all the terms in individual brackets. So it would be a bit easier to see that. Now you can repeat this exercise for any number of n a to b and any number of n b to c. Like you can say going from a to b there's 4 ways and b to c there's 5 ways. If you count individually, you'll still end up at the same result, that there's 4 times 5 or 20 ways to do this. You can do this for n a to be 100 and n b to c to be 1000, and you will still get the same result, because you can see how we've added it, right? Basically, I took one root from a to b, and then I counted the two roots from b to c. If I take the auto, then there's two possibilities. If I take the walk, then there's two possibilities. If I take the bus, then there's two possibilities. And hence, this is a to b. This, maybe I should highlight another color. This is a to c through one possibility. This is a to c from another possibility. This is a to c in the other possibility. And these individual possibilities are basically in the different ways in which you can go from a to b, right? So there's two results that we've obtained. Either you can individually add every single case to go from a to c, or you can multiply n a to b and n b to c, right? Okay, so 6 is also equal to 3 times 2 equal to n a to b times n b to c. Now these two results that we've obtained, that is either individually adding or multiplying a to b and b to c, these are consequences of the two fundamental principles of counting. The fundamental principles of counting. Now there's two fundamental principles of counting. There is one multiplication principle, now this principle states that if you have two tasks, if you have say m ways to do one task, n to do another, the both can be done, both of them can be done simultaneously in m times n ways. M times n ways. This is important, so I'll highlight it. And that is what we've done here, right? If we multiply 3 times 2, or in other words n a to b and b to c, for going from a to c we have to do two tasks simultaneously, that is going from a to b and then going from b to c. So these two tasks we have to do together, and the individual ways to do those are 3 and 2, and hence we multiply 3 times 2. Another way is, another approach that we can use is the addition principle. The other way you can approach this is by using the addition principle, which states that if you have m ways to do one task and n to do another, both, or not both actually, either one either one can be done in n m plus n ways. Either one can be done in m plus n ways. And if you look at the if you look at our example, you can understand this, because we can only go from a to b and b to c in specific ways, right? So if I take this route, this and this, I cannot take any other route simultaneously. So it's either the following routes. It's either auto plus metro, or say bus plus train, or say walk plus metro. These are all individual 6 possibilities which are separate from each other, and we cannot do s- any of these simultaneously. These are all separate cases, and hence we add 1 plus 1 plus 1 plus 1 plus 1 plus 1, 6. So these are the two fundamental principles of counting, and it is necessary to know the difference between them um, uh, before going to actual permutations and combinations, because this topic is the basis of the entire chapter. So all the formulae that we will be deriving later on are offshoots of the two fundamental principles of counting. So another way you can distinguish when to use the multiplication and addition principle are the use of two specific keywords. For the POM, or principle of multiplication, the keyword is and. I have to do task 1 and task 2. If I have to do both of them together, I have to do task 1 and task 2 and task 3 and task 4. Then I multiply all the individual ways in which those tasks can be done, and the addition principle. For this, what do you think the keyword should be? It should be or, right? If I have to do either one of the tasks, or if I have 1, 2, 3, 4, 5, 6, 7, or so many tasks, I have to do either one of them. I must add all the individual cases. So the keywords are and or. So ask yourself whenever you see a PNC problem as to what exactly do we have to do in order to count the number of ways in which the task can be done. Do we have to do two tasks simultaneously, one task 1 and task 2, or task 1 and task 2? So the theory of PNC, the fundamental principles of counting, is pretty much this. Um, it boils down to a lot of problem solving as well. So we'll learn along the way with a few examples. So let's take questions. First question is, so this is one of the most common type of questions in PNC, basically number forming. How many 10-digit numbers exist, one without repetition and two with repetition? Now this is repetition of digits. So there's 10 digits, right? 0, 1, 2, 3, 4, all the way till 9. Now let's look at the second case. Before, we have to fill 10 places, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We have to fill these 10 places. And so if I allow repetition of digits, then there's 10 ways in which you can place the first fill the first place. Now I've taken the first place to be this spot, but you can start from anywhere actually. Um, so the first place can be filled in 10 the first place can be filled in 10 ways because there's 10 digits 0 to 9, and because I'm allowing repetition, all of these ways can be filled in 10 ways. All of these places are filled in 10 ways. Now the number is made by placing all of these places filling all of these places simultaneously with digits, which means I have to fill place 1 and 2 and 3 and 4 and 5, all the way till 10. Now notice my use of the word and that is why we must use the multiplication principle to find the total number of ways to do this. So the answer will be 10 times 10 times 10, 10 multiplied 10 times, so 10 power 10. The first case is without repetition. I'll highlight the answer. You can, if you'd like to solve the problem, you can pause the video at the right time and solve it for yourself and then check later. So if you do not allow repetition, and again same as before, 10 spots. Now the first place I can fill in 10 ways because there's 10 digits, but now this digit I've used cannot be used again because there's no repetition of the same digit. So any digit cannot appear more than once. So if I've used up a digit in the first place, the second can be filled in 9 ways, 10 minus 1, third in 10 minus 1 minus 1, 8, 10, then the fourth in 10 minus 3, 7, and so on. So 5 can be filled in 6, 6 and 5, 4, 3, 2, 1. So the answer, because again we're doing all of these tasks simultaneously of filling each place with digits, the answer is 10 into 9 into 8 into 7 into 6 all the way up to 1. Now this number, this arrangement is a very special result that we'll be seeing the next lecture. So do keep in mind this specific arrangement of numbers, basically 10 into 9 into 8 into 7 all the way till 1, or any number into the product of its previous numbers. Here's another similar um, problem. Let's say I have the word space and I want to arrange this word, arrange the letters of this word to form a new word. In how many ways can I do that? So I have 5 places because 5 letters, 1, 2, 3, 4, 5. So I have to fill 5 places simultaneously. 1, 2, 3, 4, 5. Now the first place can be filled again in 5 ways because 5 digits. I've used up 1 digit, so the second can be filled in 4, third in 3, then 2 and 1. So the answer is again 5 times 4, 3, 2, 1. Similar to the result that we got here. Basically the product of all numbers up to um, 5 and 10. So 5 times 4 times 3 into 2 into 1, this is 120. Here's another example that um, perhaps will help you understand the two principles better. Very similar to the problem before, the initial problem that we saw. Okay, so there's a place A to B, and there's these possibilities to go from A to B. So each arrow represents a specific route. Now I want to know total number of ways to go from A to B. So same as the pretty much same as what we did here. Now we can obviously count each individual case and then apply the addition principle, but let's try to see a bit systematically. If you see, there are two possible subroutes to go from A to B. Either go through N or go through S, right? So if I go through N, I cannot go through S at the same time. Any route I must take must either pass through the point N or by S, or notice the use of the word or, and hence N A to B is equal to N A to N plus N A to N to B plus N A to S to B, because I must either go from A to B through N or either go from A to B through S, right? So there are these two possibilities, N A to N to B and N A to S to B. Now N A to N to B, we can calculate, we've actually calculated this before. This is the same as A to B to C, just 3 times 2 or 2 times 3. So this can be written as N A to N times N to B plus N A to S times N S to B, because if I go from A to B through N, I must go through A to N and N to B. So noticing the AND, I must use the principle of multiplication. So this is A to N, there's 2 ways, N to B 3 ways, A to S 1 way, and S to B 2 ways. So N A to N there's 2, and N to B there's 3, plus A to S 1 and S to B 2. So this is 6 plus 2 equals 8 ways. So there's 8 ways to go from S to B using the principle of multiplication and principle of addition. So first see that what are the individual possibilities of going from A to B, and then count the and then apply the multiplication principle. So 8 ways is the answer. Here's the next question. How many numbers, 4-digit numbers, that is 4-digit numbers, can be made from the numbers, or the digits rather, 2, 4, 3, 7 that do not exceed 7432. Now this is much more advanced than what we've seen before. So let's see what to do. Now 4 digits, so 1, 2, 3, 4, right? the number must not exceed 7432. So let's try to see individual possibilities of how the number can be made. The first case is if the thousands digit is occupied by the number 7. Now if the thousands digit is occupied by the number 7, this could possibly put a restriction on what the other digits could be, right? But because since I've used up 7, I only have 2 comma 4 comma 3 available. All of these numbers are less than 7, right? So any number I make 7432, so 7432 7234 7243, this will never exceed the number that we have. This will never exceed 7432. It may be equal to the number, but it will never exceed 7432. So there is no restriction on how to place 2, 4 and 3 if we already have placed 7 in the thousands digit. So the second place can be filled in 3 ways, because we have 3 digits since we've used up 1 digit. Since we used up 2 digits, the third place can be filled in 2 ways, the fourth in 1. And we've already used up the thousands digit, and we've already used up the digit 7 to fill the thousands place. So there's just one way to do that. So the total number of ways for this is 3 into 2 into 1, 6. But this does not complete the question, because this is only the case where 7 occurs in the thousands digit. But if any number that I form using 2, 4, 3, 7, this may not be the case. So the number could also be so 7 could also appear here, or it could also appear here in this place, or in this place, or even in this place. So let's see those individual possibilities. Right? 1, 2, 3, 4. Now, because I've already found the number of ways for the case where n falls in the thousands place, the second case that I'm considering here, n will fall anywhere, 7 will fall anywhere but in the thousands place. So 7 can be here or here or here, right? So this place, the first place, can be filled not in 4 ways but in 3 ways, because the number 7 is reserved for these 3 places. So this can be filled in 3 ways, this can be filled in 3 ways, this in 2 and this in 1, right? Because for the thousands digit we have 3 possibilities, 2 or 4 or 3. Now because I've already used 1, we have 2 digits left, and again we have 7. So say perhaps the first thousands digit is 2. Now I have 4, 3, 7 remaining. So this can be placed in this. If I fill up 2, there's 3 ways to fill up this place, 2 to fill up this place, and then 1 to fill up the last place. So 3 into 3 into 2 into 1. So again, because I have to do all of these tasks simultaneously of filling all the places, 3 into 3 into 2 into 1, 18. So our answer is n equal to n equal to 6 plus 18, 24. Now it would be a bit more complicated if we had the digits, say for argument's sake 2497. Say if this was the question. Now you would have to be a bit more careful, and say the task is to not exceed the number 7492. I've just replaced 3 with 9, and so let's see in this case what happens. Again, I cannot place 9 here. I cannot place 9 in the first in position 1, because that would because any number over 9000 will exceed 7492. Now if I place 7 here, there's 3 digits remaining, 492. So this number, the digit in the in position 2 now cannot be 9, because if I fill this with say 9, then the only two possibilities are 7942 and 7924, both of which exceed 7492. So we cannot count these, correct? So I can only fill the position 2 with either 4 or 2, which means two numbers. So and now if I fill any of these two digits, 4 or 2, now I have no restriction to place any digit in positions 3 and 4, because that number will never exceed 7492. So if 72, then the possibilities are 7249 or 7294, which are both less than 7492. The same will go for if you have 74 and then 29 or 92. So there's two ways to fill position 2, and because we've used up 2 digits, 3 and 4 can be filled in 2 and 1 ways. So this is 2 into 2 into 1, 4. Right, now another case is if 7 falls anywhere but in 7 falls anywhere but the thousandth place. So if 7 falls in this position or this position or this position, now the first place can be either filled with 2 comma 4, because we cannot count 7 here because we've already counted the cases for 7 here above, so, and we cannot use 9 in this place because that would exceed 7492. So this place can be filled either with 2 or 4. Two ways to do this. Since we've used up one number, and any number formed by 2 or 4 in the thousandth place will never exceed this number, there's no restriction to fill position 2, 3, 4. So I've used up one digit, which means I have 3 left for the second position. Erase and write again. One, two, three, 4. So 2 ways to fill position 1, 3 to fill 2, 2 to fill 3, and 1 to fill 4. This is 2 into 3 into 2 into 1 equal to 12. Right, so the possibilities in this case are 4 plus 12 equals 16. Now I've not used the addition, I've not used the multiplication principle for these numbers 4 and 12, because the digit 7 can either go in the thousands place or anywhere but the thousands place. It can either go here where I'm drawing the square, or here. Now because I've used or, I must use the addition principle and add those two cases, and you can see that this number is much lower than the before case, the case before. Okay, let's look at one final question. How many numbers are formed with the digits 2, 3, 4, 5, 6 that exceed 400. How many numbers formed with the digits 2, 3, 4, 5, 6 exceed 400? So there's no restriction on how many digits are there in the number, which means we must count all the possibilities. So there's the possibilities are 3-digit number, 4-digit number, or 5-digit number, because the maximum digits are 5, so the maximum digit number that can be formed is 5. If we have to form a 3-digit number, 1 2 3 1 2 3 4 1 2 3 4 5, the first position here cannot be filled with 2 or 3, cannot be filled with 2 or 3 because that would be less than 400. But if we fill this with 4, 5 or 6, then any digit we place after it would make it exceed 400. So we can fill the position 1 in 3 ways, right? Now I've used up 5 minus 1, 4. I've used up 1 digit, so I have 4 remaining. So position 2 can be filled in 4 and position 3 in 3 ways. So 3 times 3 times 4, 36. For a 4-digit number, there's no restriction on how to place the digits because a 4-digit number will always be greater than 400. So this place can be filled in 5 ways, this in 4, 3, 2. So 5 into 4 into 3 into 2, 120. And again, no restriction for the 5-digit numbers because they will again exceed 400 always. So 5, 4, 3, 2, 1, also 120. And because the number can be either a 3-digit number or 4-digit number or 5-digit number, and total is 36 plus 120 plus 120 to 76. So this is what we covered in today's lecture, the fundamental principles of counting and some basic examples of how to use the two principles. So thank you for watching.